Welcome to this session. My name is Martin. I'm glad to be here and talk to you and be able to give you a quick introduction to the topic that is very close to my heart, which is about sustainability in software engineering. So my name is Martin. I work for VMware. Usually in my day job, I work as part of the Spring core engineering team on Spring tools. So plugins for VS Code and Eclipse stuff. But today, I don't want to talk about that. I want to talk about sustainability and climate change and things that I think are very important in that topic. So for that, I will share my screen and do some few slides. The question for me is, I'm very kind of passionate about sustainability, and I'm passionate about software engineering. And in my private life, I do a lot of stuff around sustainability and thinking about purchasing renewable energies and things like that. And we all know that climate change is a big topic and that we need to do something. But the question is really, what should we do? What can we do? What is possible? And that is the question that made me think about what can I do in my day-to-day job. So what can I do as a software engineer to help fight climate change? What is the impact that I can have, basically? What can I do every day? So that is why I would like to talk about that. That's why I researched into that topic a little bit. And these are basically my results. And for the session, I would like to encourage you to ask questions in between in the chat window. Whenever there's something super important coming up in between, I think the moderator will interrupt me so that I can answer questions in between. But I will also have a slot at the end, I think the remaining 10 minutes or so, where you can unmute yourself in the end and ask questions in the end directly, if that is okay. So I hope you can see my slides, and we can get started. So I don't want to talk about if climate change is real or not, or whether climate change is there, or why is it really human-made or not. I think that is all clear, right? We don't need to discuss that anymore. The question is really, what can we do? And I think in my day-to-day job, when I think about software, and what I do all the time is, if you think about software, you can really see that software is in every aspect of our daily life, right? So not even as a software engineer, but also in the perspective of what is the impact that I can have. So software runs everywhere. So the stuff that we write as software engineers, it is really in every aspect of our lives. It runs in data centers, it runs in our pocket on the smartphone. It basically is part of everything that we do all the time. So that also makes me think about, we can have a huge impact on that, right? We have a huge impact in terms of what is software allowing us to do, what is software enabling the world to do, but it also gives us as software engineers a huge power and responsibility to be really careful about what do we do with software. And in my case here, and for the talk, what do we do with the software that we write, and how do we write those software in order to help fight climate change? I think that's a huge challenge, and it's a huge responsibility for us. And I think we should be really, really serious about that. If we think about fighting climate change, we of course need to think just quickly about what's the main driver behind the scenes, what causes the climate change. Of course, there are these greenhouse gas emissions, and the majority of the greenhouse gas emissions is carbon emissions, of course, so CO2. So there are other greenhouse gases that also affect the climate change, but I will not talk about those emissions a lot in this talk. I will mostly focus on the carbon emissions, or the carbon emission equivalent emissions in this talk. So that's kind of the main driver. So we need to take a look at that. If we want to take a look at the carbon emissions, we need to ask ourselves, where do they come from? And what is what is part of those carbon emissions, and what is the effect that we as software engineers have on carbon emissions. If we think about those carbon emissions, it's totally clear that down the road, probably already in a few years, so we don't have a lot of time left, in a few years, we need to decarbonize everything. We need to decarbonize the industry, we need to decarbonize our households, and of course, we need to decarbonize the whole world of software engineering itself, and think about different aspects in there. And if you take a look at that, it's not only the most obvious one. It is not only about, oh, the software runs in a data center. We need to take a look at the data center, and then the problem is solved. So it's really complicated if you take a look at the details. And there are many aspects there where carbon emissions being caused and being created and emitted into the atmosphere. If you take a look at that, it's of course the data centers, but it's also kind of production of the hardware that runs on our desktops in our data centers. It is the network traffic. So all the data that we transfer over the internet or over the network in-house to the data center around the globe, basically. It is memory consumption and CPU cycles, of course. So that kind of drills down, if you look into more details inside of the data center, what is affecting the energy consumption in this case, or what is causing carbon emissions inside of the data center? It's of course CPU cycles, network transfer, and memory consumption, plus the hardware production. It is heating and cooling, of course. We need to take a look at the energy production. We need to take a look at the energy consumption. We can think about shipping costs of kind of shipping hardware around. We can even think about the way we go to work. Even if we go to the office again, how do we go to the office? What's kind of the transportation that we choose, and is that transportation already fully decarbonized or not? So there are many different aspects. Of course, I cannot really cover all the aspects in this talk and dive into every detail. So I tried to pick what I think kind of maybe the most important ones, or maybe the ones with the biggest impact. And if we take a look at the carbon emissions and what is causing those carbon emissions, it is mostly caused by energy consumption and energy production. There are other aspects of that as well, and it always depends a little bit on the exact perspective, what the exact percentages of those numbers mean. But energy is a big driver here, especially if we take a look at the software engineering world and running software. So if we look at that, there is sometimes these super quick answer about, oh, it's all about the energy production. So we need to get to 100% renewable energy, and then the problem is solved, right? So let's just wait, sit back, and see. Someone else will take care of that, right? Someone else will deal with that. Someone else will make all the power that we need in a renewable way. So we don't need to do anything, right? I think that is true to a certain degree, but it's not the full story here, because it is reducing the discussion down to the electricity that is used. It's not looking at the supply chain. It's not looking at the hardware. It's not looking at transport. It's probably not even looking at data transfer around the globe. And on the other side, it is just looking at the one side, at the energy production side here, because we don't have 100% renewable energy to power everything at the moment, right? So it will take a long time until we reach this goal to have 100% renewable energy for everything that we do on the planet, in our country, in our city. The same is true for data centers, right? So even if data centers are if they say we run on 100% renewable energy, this renewable energy is being produced somewhere, but it is not it is not enough to power everything on renewable energy. So if you put all the renewable energy into the data center, it is missing somewhere else in the system, right? So you cannot really look at the data center individually and say, okay, this data center runs on renewable energy and the problem is solved, right? So you need to look at that from both sides, I think. You need to look at that from increasing the total amount of renewable energy that you put into the system, not only on the data center, but into the system. And on the other side, you need to decrease the energy consumption so that you can get there faster. If you just wait for the 100% renewable energy, it will be too late, right? If we think about these curves, about the energy consumption in data centers, the curve goes up, right? We do more and more in data centers. And even if they get more efficient over time, you can do a lot of stuff now that you maybe couldn't do 10 years ago with the same amount of energy. So it gets more energy efficient, but it is still increasing, right? The total energy consumption is increasing. And if you think about the carbon emissions and the equivalent of the carbon emissions that the industry produces, if we think about the data centers and internet usage, so network transfer, we are already in the same ballpark than the airline industry. So we are not talking about a niche. We are not talking about a small thing that we contribute with software and data centers to the overall carbon emissions on the world. It is a big chunk, right? And it is increasing. There are predictions that probably 10% of the overall energy production on the planet will be used in a few years for data centers and for dealing with data, and which basically means running software, right? So if we can turn the knob on the software side and make that really efficient, make the software produce less carbon emissions, we can have a big impact. And that big impact is sometimes, it looks, when you take a look at that, it looks small, right? It looks so tiny. If you think about, oh, how many watts do I really need to run this software in a data center, for example? But if you take a more holistic view on that, you will see that if you put, let's say, 100 watts of total energy into the system, in the end, for running your software, there's only kind of something like 5 watts left that you can really use for computing, for running your software on the hardware. So a lot of that stuff is just wasted along the way, like for cooling, for operating, for electricity generation, and stuff like that. Which also means, if you turn that upside down, that if you can reduce the usage, for example, in this case, from 5 watts to 2.5 watts, it means that down the line, you have to put 50 watts less energy into the system, right? So it scales up quite a bit. So don't be irritated about when we chat about saving a few watts here and saving a few watts there. It has an impact, and it has a dramatic impact if you look at the data centers and all the other places where basically we run our software. So let's jump over the other side. Let's take a look at the energy consumption. So what does the energy consumption look like, and what can we do about that? And what makes sense actually to do that? We can look at, again, all the different aspects, right? But I'm not able to do that in this talk. So I pick and choose a few. I pick hardware, I pick network, I pick CPU cycles and things like that. So going down a little bit the path of the data centers and what is caused by our software. And whenever I thought about that, and if you look at all the details, they can be quite complicated. And they can be very detailed and very kind of drilling down into many different aspects. And what does it actually really mean? And what can it really do if I squeeze out this little bit. So I thought about over time trying to come up with something like a rule of thumb, right? Just a general rule about what should I keep in mind day to day when I implement and when I realize, when I engineer software. And the simple, and of course, the super simplistic version, right? It doesn't cover everything, but it's kind of a general rule of thumb. I think it's quite useful to think about to run your software with less hardware. I think that is a nice and easy to use rule of thumb. Just try that, right? A lot of the following discussions will kind of fall under this umbrella and will be covered if you think about use less hardware, right? If you deploy your software in a data center on some public cloud, think about, do I really need these big instances, or can I use a smaller instance? Can I use less memory? Can I use less CPU cycles? Sometimes it's so easy to press the button and say, I'm not exactly sure, let's use the slightly bigger version of that instance. Let's use a few more instances just to be sure. Or maybe it's cheaper to say, let's buy the bigger instance instead of investing the time to make the software more efficient. And then you run bigger instances in the cloud. But in the end, maybe it's cheaper for you, or I'm not even sure if that's cheaper, but it will cause more emissions down the road. So if we think about that, of course, the step number one, when you think about, let's try to use less hardware, is use virtualization. A no-brainer, right? Everybody's doing that. Of course, it makes the usage of the hardware more efficient. So you buy basically less hardware because you can use it in a better way. And hardware production is actually also quite an important factor in the equation. So buying less hardware makes a difference, right? Buying less. Don't buy a new machine all the time. Don't buy, maybe at home, you can even transfer that at home. Don't buy a new laptop and the latest and greatest all the time. The production of this stuff, it consumes energy, it causes emissions. So buying less makes a difference. And the next step is, and that sounds maybe a bit stupid, is do not run your software. Why should I realize software if the advice is do not run the software? We write software to run it, of course. So sounds a bit weird. But if you take a look at data, at real data behind the scenes, you will see that software is sometimes is running. It's deployed on the public cloud. It's deployed in your data center. It runs somewhere. It does stuff, but nobody's using it. Why do you? And even if you deploy that and nobody's using it, it is consuming a significant amount of power, reserving an amount of space on the hardware, and therefore causing a lot of emissions. And even if you think about, yeah, you can scale down the CPU and it doesn't consume so much energy if the software is actually not doing anything and stuff like that. That is true, of course. But if you look at the data center operations, you will see that you cannot really reduce the energy consumption in a data center down to zero if you have all the software running on the data center and everything runs, everything is deployed, but nobody's using it, right? It will still consume maybe about 50%, very rough number, 50% of the energy. So not using the software and running the software, if nobody's using it, doesn't make a lot of sense. So you need to take a look at that and kind of think about these scale to zero ideas and architectures. Maybe when you start to implement software, it can really make a difference. And it sounds a bit weird, and it sounds a bit strange, but in reality, it is a big problem. It is really a giant problem. VMware, for example, they consolidated the data center back in 2019 in Singapore. they had just to move the data center, so they were just consolidating it and then just looking at every single piece that is running on the data center. And they figured out that 2/3, 66%, around about 2/3 of everything that was running on the data center was not used anymore. So 2/3 of the whole data center was not used. So this is a real problem, right? This is not just a stupid idea, or think about, oh yeah, yeah, of course nobody deploys software that no one's using. It's reality, right? That's really happening. And you of course can think about that as, oh yeah, it's a VMware data center. So VMware is doing virtualization. So of course they have a lot of testing stuff that whatever. Is that really the case for other companies as well? It is. So there's a study from a researcher from Research Institute and someone from Stanford University, I think, looking at many data centers. I think it was kind of about 16,000 or so, or 16,000 machines in total. I don't remember the exact number, but it was kind of looking at a broad scale of data centers, a broad scale of machines running across companies, across different data centers, things like that. And what they figured out is that round about between 25 and 30% of all the physical machines were zombies. So they were not used, right? Not used at all. There was software deployed to that, but the system was not used. Zero over a period of, I think they tracked down a period of 6 months, right? Zero usage, but it was still running, consuming space, consuming energy, and consuming quite a significant amount of energy. So that is a problem. And that alone is, I think, a dramatic number. If you think about kind of maybe 1/4, 1/3. But if you think about the next category that they analyzed, the next category is about stuff that is being active for less than 5% of the time. Active means actually really doing something, right? Network activity, disk activity, whatever, actually doing something, right? And that these between 0 and 5% was another third of all the deployed workloads. So another third. So you can, again, you are very close. You reach this number of 2/3 of all the stuff that runs in the data centers were more or less useless, right? Running, consuming space, consuming energy, and consuming a significant amount of energy. So if you think about that, try to remember, maybe you also deployed something somewhere for kind of a testing purpose, for trying something out, for deploying some version of your system, and that is not, it's maybe not used anymore and not needed anymore, but it's still sitting there. It's maybe doesn't cost a lot of money, but it costs a lot of energy, and it's causing a lot of emissions. So think about those zombies. It really makes sense to keep a close eye on that and maybe come up with ideas how to automate the elimination of those, and think about the scale to zero aspects. Of course, then the next step is, if you want to run your software actually, what do you do about that? So if you think about that, memory, for example, consumes energy. It sounds a bit weird, maybe in the first place. I was a little bit surprised to see that, but if you just say, okay, I reserve memory if I deploy my stuff to the public cloud or in a data center, and I need a 1 GB of RAM, which is not a lot, right? Many people say, yeah, 1 GB, what's that? Let's say 16, let's say 32, let's say 100 GB or whatever of RAM, because I have such a huge application. That even if you don't do anything with that memory, it consumes a constant amount of energy. That is something. It is significant. If you add the CPU cycles to that, of course, more stuff adds to the equation. So when you think about that, really think about reducing memory consumption, and reducing CPU consumption. So if you deploy your stuff in the data center, really think about those specifications of your software and think about squeezing it down, trying to use less. It makes sense. Down the road, it is most likely also a nice win-win situation, because consuming less resources in the data center makes it also cheaper for you. Maybe, I don't know, depending on where you run your stuff, if it's a lot cheaper or just a little bit cheaper, but it is cheaper. So that's good. So you don't really have to pay a lot for that. And it makes a difference. So if you think about, for example, comparing that to the airline industry again, and that's what many people have in mind when they think about those situations and think about climate change and think about carbon emissions. They have the rough idea about, okay, going on a plane for transatlantic flight. In this case, I chose Frankfurt to San Francisco. That's not a good thing, right? You should not really do that if it's not really necessary. It will produce a lot of carbon emissions. If you put that into the equation and kind of compare that to what we talk about in the data centers, if you have, for example, one of these racks in a data center, and the Dell one here is just an example for that. If you calculate that down, it's about the same carbon emissions that is being produced by this piece in the data center than one transatlantic flight. So if you think about, and this is not a lot, right? It's 32 gigabytes of RAM, 2 CPUs. So that's not a giant thing. That's something that many applications in a data center easily consume without asking for it, right? Of course, you just click the button and you get tens of those or hundreds of those, right? It is every single thing will produce one transatlantic flight, and it's around about the same carbon emissions. So it makes clear that it has an impact, and the numbers are quite significant. So it makes sense to think about those numbers and think about your software and the way you write the software, and especially the way you run the software. It is really important. Of course, when one example that we do as part of the Spring Core engineering team, we also think about that, and we think about running stuff more efficiently. So can we make something like Spring Boot or Spring applications being able to consume less energy and down the road also produce less carbon emissions if you run them somewhere? And we are experimenting and combining this with the GraalVM native image technology that you probably heard about. So you can just ahead of time compile the application down to a native executable. You don't need a JavaVM at runtime anymore, and you get a super fast startup. And you, in general, those natively compiled Java applications use a lot less memory for various reasons. So that is interesting. And it allows you, especially due to these super quick startup times, to really think about these scale to zero architectures, because you cannot really kick something up if it takes seconds to start up. If it has just milliseconds, then you really start to think about it, right? So it's an enabler for this kind of thing, and we are kind of investing quite a bit of time and engineering power to make that possible, and especially to think about, can we make this possible using the GraalVM native image technology from Oracle and from that research team? Can we enable that for basically all the Spring applications that are out there in the world? And there are millions of Spring applications, and especially Spring Boot applications, running in data centers around the globe and running everywhere. So what we are trying to do is enable software engineers in the world to use this technology, the native image technology, with their existing Spring Boot applications to kind of turn the knob, switch them to a native executable, let them run in the same way as before, but consuming less hardware, consuming less energy, less memory, less CPU cycles, probably. Could be a huge enabler. And the interesting piece here is that you don't you don't really need to rewrite your application to do that, right? You don't really need to switch to another framework, switch to another language, switch to another runtime, basically. You can still consume all the and benefit from all the great Spring Boot programming model, the community, the libraries that are out there, all of the stuff that you're very familiar with, and combine that with this technology. So I think this is kind of one thing that we are, for example, doing in order to kind of push the needle towards using less than instead of using more. And I think that this is a great example, but it should not stop you from thinking about your own activities and the stuff that you can do to actually consume less power in your software engineering world. So of course, then, if you think about developing your software, how much space and memory do I need? What's really kind of the size? Do I really need to run it? Or when do I need to run it? The question is where to run the software. That's, of course, the next logical question. We talked about, and I mentioned data centers quite a bit already. So the next question is where to run the software. And choosing the data center is interesting. And it's quite a challenge. If you think about, if you look into, for example, running stuff in your own on-prem, your own hosted data center, right? You should start to think about how is that being operated? How efficient is that data center? Is it powered by renewable energy? And things like that. The same applies to if you go to the public cloud and run that in a public infrastructure as a service. Which cloud to use, which data center exactly to pitch, which region to choose, because all the regions and all the data centers, they have different characteristics in terms of renewable energy and power consumption. Sometimes you see the big label on top of them saying powered by 100% renewable energy or being carbon neutral. And that is usually, that at the moment, that usually means that the company behind the data center is purchasing renewable energy from a renewable energy provider in the same amount than the data center is consuming in a specific time, right? In a month, in a year, whatever, right? So they purchase renewable energy in the same amount. But it does not mean that the energy that is consumed in the data center is actually coming from a renewable energy source all the time, right? Because usually the renewable energy is not available on those data centers all the time in the same amount that actually the data center needs the energy, the stuff that the energy consumes. So there are gaps. And filling these gaps and making data centers that are running on renewable energy all the time, exclusively all the time, is really complicated and will take maybe another decade actually to do that. I think Google announced something like the goal is for it 2030 to achieve that. And maybe they're faster, I don't know, but it's nothing that we have at the moment. So another data point that makes it very clear that thinking about the energy consumption side also makes a lot of sense. But going back to where to choose and which data center to choose, it's interesting because you can actually figure out there are APIs for that, where you can figure out that what's the energy mix in a certain region where the data center is being operated. At a certain point in time. That way, you can do things like figuring out what's the best region to run the software at a given time, for example. Maybe think about data centers in cooler regions of the world, so less cooling is needed, things like that. And there's for example, if you think about, of course, everybody's running Kubernetes these days, and everything runs on Kubernetes, right? Or everybody wants to run everything in Kubernetes. There's this concept of the scheduler in Kubernetes, and there's an interesting research approach to think about the scheduler in Kubernetes. So the one basically algorithm decides where to run your stuff in the cluster, can be enhanced to take this API into account and take the energy mix into account to automatically schedule your workloads onto a data center or where it makes sense, depending on the energy mix. So I think a very, very interesting approach. Oh, there was a question in the chat. I see, is it the carbon emissions per passenger? Yes, that's per passenger per flight. One flight, not so one-way flight, right? Not return. And the last resort, if you think about these carbon emissions and you think about you don't have enough renewable energy at the moment, or in the supply chain there are carbon emissions being caused down the road. So what many companies are doing is they offset their emissions. So they buy credits, basically. They buy carbon emission credits. And you can do that yourself at home, right? You can go to a company that is doing these carbon offsetting and is offering carbon offsetting, and you can buy those credits for running your heating system at home, or offsetting your holiday trip, your last holiday trip, or things like that. And companies doing that on a big scale. For example, if they are not able to purchase enough renewable energy, or if they do business travel and things like that. So you can think about that. And that's actually, that's not a bad thing. Sometimes it's kind of falsely advertised as kind of greenwashing, or maybe not advertised, but kind of people judge about that as greenwashing, which I think it is not. But you should take a look at the details. And if you look into the details of those offsetting things, there's usually there kind of two categories of offsetting approaches that you can choose. And I think you should, if you want to do that, which is a good thing, so I would like to encourage you to do that. But I would also like to encourage you to take a closer look and kind of pick the right offsetting projects and the right offsetting companies for that. So one thing is, for example, they invest in projects that avoid carbon emissions in the future somewhere in the world, right? For example, they go to developing countries, and they support projects where they support local communities with specific technology or with specific things, so that they don't, for example, don't burn all the wood in the future, or can do stuff in a more energy efficient way, which is a great thing, right? But it is not what you might think about carbon offsetting is. It is not extracting the carbon emissions that you put into the atmosphere by going on a plane or for whatever reason. It's not extracting that from the atmosphere again. So it is in the atmosphere. You put that in, right? And it's not extracting that out. It is just avoiding additional emissions in the same amount in the future. Should have that in mind. There are other projects that are actively trying to reduce carbon emissions from the atmosphere again and try to bind them somewhere. Of course, the most famous one is planting trees, the most kind of natural way of extracting carbon emissions from the atmosphere. And this is, again, this is a great effort. And we should do that, right? No question about that. But you should also keep in mind that this is the calculation behind that is usually, it's a bit difficult, because you put carbon emissions into the atmosphere now and you plant trees for that, right? But those tree planting is calculated usually between 40 and 100 years. So in 40 or 100 years, those trees that basically you planted extracted the carbon emissions from the atmosphere again in 40 or 100 years. So we don't have that time. So and you cannot really speed that up a lot instead of just planting more trees. So it is a good thing. We should do it, but it's not really a solution for not reducing the carbon emissions. I think that is super important, right? So the first approach is always we need to decarbonize everything. And just for a very, very tiny little few cases, this offsetting really makes sense in the meantime, but it is not really a solution. With that, I kind of come to an end on time. So we have still plenty of time for questions and maybe some answers. I think if we really think about these climate change and software engineering in a serious way, we will see a lot of innovation happening in the next few years, I think, and probably in the next decade. So I think it will be an important factor for software. How do you run that? How do you write that? And what is kind of the carbon emission price tag that is on the software? And it might be a big market differentiator in the future. If you say, hey, if you use this software, it really runs on 100% renewable energy and it consumes a lot less energy than your competitor, for example, that maybe has software that causes more carbon emissions. So I think that will be a huge landscape full of innovation and huge possibilities for us as software engineers. So let's go for it. And with that, a few references where you can find more details. I will share the slides, and I thank you all for joining and for watching. And with that, I think I will just stop my screen sharing, and I would be happy to answer a few questions if you have any. So if you have questions, unmute yourself, and I will try to give answers to them, and I would be very happy to do that. So please, hope you enjoyed the session, by the way. So very interesting. Thank you. First comment. Thanks for the nice feedback. Always appreciate it. Are there any questions or any topics you want to talk about or you want to discuss maybe? Always happy to dive into a few more details. Right.
Yeah, one question.
Yeah.
Hi, it was interesting session, first of all.
Thank you.
One thing I would like to know, like for Bitcoin mining, they are using a lot of ungreen energy, I would say. What is your thoughts about it? Like a lot of people are talking about it for crypto mining, use of electricity, and wastage of electricity. So what are your thoughts?
It's insane. It's totally insane to use that all that amount of electricity to do these Bitcoin mining, and just I'm not an expert on cryptocurrencies, things like that, and they might be useful. So I cannot really judge that kind of that sector, right? But I think if you really think about that seriously, I think the important piece is, if you want to do that, don't go out for kind of a country where you can buy super cheap energy from burning coal or gas to do these crypto mining things or whatever. Go somewhere where you can run all the stuff on renewable energy, and maybe think about putting that first and say, hey, maybe that is kind of a business opportunity for people out there saying, hey, I offer crypto mining, but my crypto mining is I built up the solar array or whatever for that, so it runs on renewable energy all the time. So I think that's the main factor in there, since we need to decarbonize all the stuff. So we also need to decarbonize crypto mining, basically. Yeah. So if you're interested in that, please don't go to the cheap coal burning folks and run it there. Choose it wisely.
Yeah, makes sense. Thank you.
More questions? Thanks for the question, by the way. Another one on the chat. Great talk. Thank you. Thanks for that. How do GraalVM native images compare to native languages like Rust? Interesting question. I don't have exact numbers. I know that Java in general, even without the native image compilation technology, is playing relatively well compared to other languages in terms of energy consumption. There's a research paper out there comparing basically hundreds of languages and ranking them in terms of their energy efficiency. And Java is I think among the top 5 or so, which was a bit surprising to me. I thought that, oh yeah, of course, all these natively compiled ones are much higher, and C and C++ and whatever. And I don't have the exact ranking in mind, but Java was actually pretty good. So I think that that's just the assumption that I draw from combining those two worlds. I think using the native image technology from GraalVM, my assumption would be it is equally good as every other natively compiled language, maybe even better, because it was already quite good running on the JVM. But if you're interested, I would encourage you to take a look at this research paper comparing the energy efficiency across languages. Of course, the GraalVM technology is not in there yet, but I think that gives you a good idea about how languages in general compare, which I think was quite interesting and surprising. So thanks for the question on the chat. More questions, more thoughts around that. So when I look on the side, there's my chat window. Don't see any more stuff on the chat. And if there are no more questions from the audience, no more questions? Okay, cool. Thank you all for coming. Thanks for listening. Thanks for joining the session. Please give you a thumbs up or your rating to the session on the conference page. And thanks for joining. Hope you enjoy the rest of the conference. Thanks a lot.